Hello, good morning. Here we are for part 1 of lecture 17 of CENG 4412 Steel and Concrete Design. Today we're going to continue on discussing some elements of structural steel columns, looking at some aspects of local buckling, slenderness, built-up members, etc. Okay, so I want to discuss some elements of this. In particular, I want to look at local buckling or describe local buckling, describe stiffened and unstiffened plate elements in compression, define column compactness, and the effect of this on overall capacity, the effect of local buckling on column strength. So we know that from when we looked at, for example, beam design, there were both compact and non-compact, compact and slender elements of structural shapes. So, and really, steel columns are going to behave very similar to steel beams. So previously, we looked at critical column lengths. We considered critical column lengths, critical column lengths or critical column stresses, elastic and inelastic buckling. But everything we looked at was in section E3 of the steel manual. So we were looking at section E3. We're discussing through section E3 of the steel manual. And but let's look at this in detail. Let's look at the title of this. What does this mean? If you look on page 16.1-35 of the 15th edition, or at least my printing of it, you have a section titled E3, flexural buckling of members without slender elements. Without slender elements. So looking at the flexural buckling of members without slender elements. And this is where we have, so again here we look at the, this is very similar to what we had last time, where we have a chart of really effective length, which is K, which is the LC they discuss, where LC is again equal to KL over R, or just KL. So you have these two regions. You have equation basically E3-2, something like this. This is equation E3-2. You have some very stubby columns or compact columns where equation E3-2 governs, and then below that, or above that range, I suppose I should say, you have equation I guess that's going to be E3-3. E3-3. And the transition region of KL over R there is going to be the transition stress, or sorry, I shouldn't say transition stress, the transition length is going to be where LC over R is less than or actually is equal to, in this context, 4.71 square root of E over Fy. Square root of E over Fy. So flexural buckling of members without slender elements. So we need to look very closely at this. What about this term here? Slender elements. Slender elements. And also elements is a keyword. So we've learned previously that we can have both global and local failure. Global versus local section failure. In global failure, the entire section is failing all at once. The entire section is failing all at once. So you're loading up to a certain point where one of the basically one of the factors, one of the section properties as a whole reaches the limit. The entire section, I shouldn't say that, the entire section fails all at once. At a certain limit, the entire section property, or the section, reaches the limit of some critical section property. Of some critical section property. And that could be something like, oh, I don't know, the area, the moment of inertia, the elastic section modulus, the plastic section modulus, the radius of gyration, etc. So depending on what you're dealing with, you're basically given a certain capacity, or depending on your failure mode, whether you're talking about bending, whether you're talking about tension, whether you're talking about compression, you reach a limit where the section, it no longer has any extra capacity on the basis of a certain section property. And that is the essence of global failure. That is the basis of global failure at the 10,000 foot view. Local failure, what we call local failure, is where one single part of a cross-section, one single element of a cross-section fails. Local failure, again, this is kind of a review. Local failure is where just one element of a cross-section fails. So just one element of where a just one single element of a cross-section fails. And examples of elements, when we talk about elements here, of course, of elements, this word element, well, what we're talking about mainly, of course, is the top flange, the bottom flange, or the web. Or the web. Those are your three main examples of elements in a section, in our common steel sections. So if we have an I shape, basically the web could be slender or compact, the flanges could be slender or compact, etc. And you could get local failure in this region here, in this region here, in this region here, long before you reach the overall capacity of the section. So kind of as a review, let me also give you a really good example of what this might mean. Where you might have maybe a very intuitive example of a local failure. Okay, so let's consider this for a moment. Let's say we had, now the example I'm going to give is in bending, not in compression, but this is a very easy way to demonstrate what we mean by local versus global failure. If you're having any trouble remembering this, example of local failure. And the best way to illustrate this would probably be something like bending. Buckling in maybe some sort of web buckling or web crippling in bending. A failure of a web in bending. So for example, imagine I build up a section. So I build up a section out of, I don't know, steel plate, just regular old steel plate. And I go ahead and give it just massive, massive proportions, but with a deliberately incredibly skinny web. So this is me basically trying to build a section deliberately with the intention of it failing in some local failure mode. So let's say maybe I did dimensions like this. Let's say I make the flanges 2 inches thick, so 2-inch thick plate and 2-inch plate. And then I make the web completely, utterly mismatched, and I make this 1/8 inch plate. You would have to be crazy to build something like this, but let's say you did. And then dimensions, let's say I make this thing, oh, I don't know, let's make this thing 3 feet by 12 feet. So an absolutely ridiculous KL over R on this thing, at least on the web there. Maybe this is 12 feet high, just a massively tall section. So this would be an incredibly foolish way to build. This is I'm thinking of, I'm trying to, yeah, I'm getting some strange looks from some people, but basically the idea behind this ridiculous beam is that I'm trying to size a beam deliberately to, that I could very obviously say, this is gonna fail in some sort of local failure mode. You would never actually build something like this. So please don't build this and then try to sue me, because you're gonna have a very bad time. Anyway, so don't build this, you're gonna ruin somebody's day. You're gonna ruin your day. So anyway, the problem with this is if you actually go and calculate the bending moment capacity of this thing, you'll find this thing actually has a decently strong bending moment capacity. So for example, if you look at this just from the point of view of a couple or something like that, this would be, well, let's see, if we could calculate the fully plastic moment capacity, multiply 2 inches by 2 inches by 36 inches, and that by the distance here at 12 feet, you would calculate an enormous overall bending capacity. Enormous moment capacity. The shear would definitely leave something to want or to desire. The shear might cause failure because this is relatively low. This would definitely fail in shear before it failed in moment. Shear is nowhere near proportional to moment in terms of shear capacity. Moment, but think about this here. Imagine I apply a point load to this beam. Let's say this beam is supporting a very large point load P. What's going to happen is, long before this thing ever reaches its full moment capacity, probably even before it reaches its full, how should I say, even before it reaches its full shear capacity, it's going to fail as a column. The web is basically going to fail as a column. It reaches before the, I shouldn't use the word web, just it, but long before the beam as a whole reaches its full moment capacity, the web will buckle. And let me explain why that is. So at first, I don't know if this seems odd to you, but it may seem, at first this always seemed a little bit odd to me. And the reason it kind of seems odd in some cases is because if you look at this, you might think, wait a minute, how can something buckle? It's not a column. I mean, it's clearly attached all the way along the way. So shouldn't it be able to disperse load up and down the web? I mean, how can something that it's not a standalone column? I mean, when I draw it this way, it looks like a column. I mean, but how can this thing buckle? It's not a column. It's a long plate. So how does it buckle? Well, let me illustrate how loads and stress will actually distribute within the web of a beam here. So if I look at a beam here, let me look at it from the side. Let's look at this from the side, from the side. This connects back up with the whole web crippling and things, and beam seats and things like that we discussed previously. Local stiffeners, that kind of thing. If we look at a beam from the side, when I apply a load P on this thing, a point load, Obviously, the stress can't be carried all at a single point. Stress has to distribute throughout the member. So what really happens here is, well, first of all, the point load, when we call something a point load, it's not truly a point load. In reality, it's actually going to be distributed over a small length. Maybe it's whatever the width of the actual thing that's laying on top of the beam is. That could, if it's a 6-inch wide, beam laying on top of this girder, then the initial width of this thing would be 6 inches or something. But as this stress distributes down, it's going to distribute down at an angle. So it's going to go something like this, usually at a 45-degree angle. Usually at a 45-degree angle, and then it will cross the flange there. So usually this is at a 45-degree angle. Usually a 45-degree angle. And the whole idea is this, the reason I'm illustrating this is, this is the only part of the element that is, of this beam that is actually experiencing any stress from the point load. Well, I shouldn't say not experiencing any stress. Obviously, the whole beam is going to go under bending and that kind of thing. But in terms of, just in terms of feeling the actual axial stress here, or the vertical stress from this, or maybe I should say the shear, this is how it gets distributed throughout the entire beam. This portion of the beam is what actually ends up feeling the stress of that point load, and then has to distribute it to the rest of the member. So it has to be distributed through this is sort of a local stress. This is what happens, this point load has to distribute throughout the rest of the member. And because of this, the entire beam is not going to be able to resist the vertical force of this point load. Only this portion of the beam has to do that. So in turn, you basically have a what this comes down to is, you effectively have a very weirdly shaped column. Inside every beam, whenever you apply a point load, you effectively have a very weirdly shaped column. It's kind of shaped like this. Imagine making a column, I'm doing air quotes, column, shaped like this, and then with a very, and this is what it looks like from the side, or from the edge, but then from the middle of the cross section, it would look just like, the beam itself. It would look like this here. So calculating the actual buckling capacity of this thing, and well, this is also complicated by the fact that the edges will also want to prevent this thing from buckling so it's more effectively braced, but this is still basically a column. This is a column with a finite cross-section, and this thing can buckle. So because of this, this is how webs are able to buckle. Even though they are continuously braced, they are still be able to buckle. Stress is not distributed uniformly. Stress can be localized. And this can cause buckling. And shear in the beam, raw shear in the beam, causes a similar effect. Well, this is how buckling, let me also discuss how it would buckle for shear. When a web is buckling through shear, the failure mechanism of this, failure mechanism for buckling under shear, is very similar. Basically, if you imagine this, if you think about this, in order for a portion of a web to buckle under shear, well, it's going to have to tear away from its bracing. So imagine a web, a portion of a web as a, imagine a portion of a web as a column. Imagine this as a column, except it is a continuously braced column. A web is basically a continuously braced column. So this would be this would be basically if I look at the shear here, this is basically, I'm drawing the web over some width. A web is is effectively a rectangular column of some width with a thickness with a thickness equal to the web thickness. And now it is a continuously braced column. Because it is continuously, that section of the section of the web that would fail under buckling is braced by other sections of the web all the way along the way. It is a continuously braced web or column. However, bracing does not have infinite capacity. But bracing does not have infinite capacity. I can't connect a big steel column to a beam made of cardboard and say that the column is now braced somewhere in the middle. That, of course, is not possible. But bracing, again, so it's a continuously braced column, but bracing has a finite capacity. If the shear in a web exceeds this bracing capacity, the web will buckle. And I'll discuss this in the context with beams, but the same thing is possible for columns. The web will buckle. And we could talk about this. Basically, all I'm trying to give you here is a sort of intuitive or mechanical understanding of how local buckling works. So let's look at this now in terms of column buckling. So column local buckling in column local buckling, when the entire section is loaded, it is possible for one of the elements to buckle before the whole thing does. Element to buckle before the rest does. The rest of the section. So for example, imagine a wide flange shape. Imagine a wide flange shape. It's effectively made of, well, depending on your perspective, either 3 or 5 elements. I guess I could say 5 elements even. Let me draw it as 5 elements. Two cantilevered flanges, and a center web. So I effectively have 5 elements here. And let's draw it like this, maybe. Oh, that's not drawn quite right. Oh, I've ruined everything forever. Lovely. Okay, I have a mutated W section now. But still we can now see the 5 elements. So basically I have 4 cantilevered flanges and the center web. This basically, a W section is basically 5 independent columns. A W section can be interpreted or wide flange shape, section can be interpreted or thought of, or I'll say interpreted because that makes me sound more intelligent. Can be not thought of, but interpreted. Makes me sound smarter. Can be interpreted as 5 independent columns, each continuously braced. So we know that the column capacity is dependent on the braced length. Each independently braced, or each continuously braced by the other pieces. By the other columns, or the adjacent column. So when I put a wide flange shape under compression, yes, it obviously does work together as one uniform shape, but you can also think of it as, and so you'll have one global moment of inertia, and that usually predicts when the whole thing will fail under global buckling. But you can also think of this as 5 independent tiny columns continuously braced. But as we've discussed, bracing does not have infinite capacity. So again, if I build a column, if I build a big steel column and I put a big steel beam coming into it, well, that's probably going to be a very effective brace, and that will reduce. For example, if I have a big strong steel column here, or a steel column here, maybe I'll do something like this here. And into this, I connect a beam. I'm ignoring the connection details here and just showing it butting up against it. This is definitely going to serve as a major brace to this thing. So, again, when column strength is dependent not just on length but on brace length, it's very similar to beams. And so, if you have a column and you apply a load to it, well, if your supports are like this, it will buckle like this. But if I brace it in the middle, then it's going to have a S-curve for buckling, more of an S-shaped curve for buckling. I'm forcing it to go to the second failure mode of buckling. And we kind of discussed that a bit last time. So whenever you brace something, you reduce the tendency to buckle. So again, when you brace something, you reduce the tendency to buckle. And continuous bracing basically eliminates buckling. But only if the bracing is strong enough. No brace is infinitely strong, especially for a brace that is nothing more than another element of the steel column, of the steel section, is sufficiently strong. So no brace is infinitely strong. Again, on this example, if I have a steel column and I bring in an enormous steel beam and connect it up very good and proper to that, well, yes, that's going to act as a big, strong, proper brace. That the column is not going to buckle at that location. However, if I connect it with something, disproportionately strong or disproportionate, not of compatible strength. So, for example, if I have a huge W36 really strong A992 steel column and I connect to it this tiny little baby, 3-inch angle to the thing, well, I'm really not going to be able to say that's fully braced that location. Or obviously, in the even more extreme case, if I were to attach a tiny 2x4 to the side of it, well, that's really not serving as adequate bracing at that point. It is a quote unquote, we could still call it a quote unquote brace, but a tiny 2x4 is not really going to do much to prevent a incredibly massive, strong W36 monster column from buckling. If that big W36 wants to buckle, that little 2x4 is just going to have to get out of the way. It's not going to really be able to do much to prevent buckling of the larger column. And in the same way, just like a little 2x4 is not going to be able to, now again, this is not that same ratio, like the internal elements of our column here, they are actually proportionate to each other, but there can be cases where before you reach your ultimate load in buckling, one of the elements will fail before that. And this is really what we mean when we say a slender element. A slender element here is basically one that is, if a section has a slender element, essentially what that means is that it will have some local failure, a local buckling failure, before, in compression for columns, we call a section slender if one of the elements will buckle before the overall section reaches its ultimate strength. Its ultimate buckling capacity. Yielding or buckling capacity. In other words, in other words, where this occurs or when this occurs, i.e., the section, the bracing capacity of one element exceeds basically the load. The load on an element exceeds the bracing capacity of the adjacent element. Exceeds the bracing capacity of another element. The bracing capacity of the element it is attached to. It exceeds the bracing capacity of the element it is attached to. So again, we can come back to our section here. Thinking of a W section as 5 independent little columns, each connected to one and braced by one another. Each connected and braced by one another. So, in other words, this flange here is braced by the web here. This flange here is braced by the web. And the web itself is braced by the 4 flanges working together. And so, if but again, this web is a column, this flange piece is a column, this flange piece is a column. These are 5 columns, and each of them are under axial load. And, guys, okay, each of them is under axial load. And if that axial load exceeds a certain point, past a certain point, perhaps even before the overall section reaches its global buckling load, it will tear away from the bracing capacity of its continuous brace. Again, just like we said, a 2x4 cannot brace a giant W36. Well, this is not such a ridiculous mismatch, but it is possible that this thing will tear away, will exceed the buckling capacity of the web before this thing actually reaches, the overall thing actually reaches its global buckling capacity. So bonds do not have infinite strength. Adjacent elements do not have infinite bracing capacity. Nothing is infinitely strong. And if you're relying on one element to effectively brace another element, as a sort of continuously supported column, there are times when that doesn't work and you get local failing. Now, you'll get local failure. Now, this doesn't usually occur. Most elements are in fact compact rather than slender, but there are times that this does happen. Okay. So let's see this. Let's take a look at how. So how do we actually determine when a section has slender elements? So slender elements, determining slender elements. Now, for beams, we had both compact, non-compact, and slender. We had compact, non-compact, and slender. And slender. For columns, we only have two categories. We only have slender and non-slender. So it's a little bit simpler. And non-slender. We only have slender and non-slender. And where this is found in table B 4.1a. So we already looked at this table a little bit before, looking at the version table B 4.1b when we were looking at beams, but this is table B 4.1a, the first section of this table. This is width, and this is described as width to thickness ratios, compression elements for members subject to axial compression. And there are all sorts of different cases here, and let's look at the first case. Case 1 is, this says the flanges of rolled eye-shaped sections, plates projecting from rolled eye-shaped sections, outstanding legs of pairs of angles connected with continuous contact, flanges of channels, and flanges of T's. So basically, if we look at, I'll look at the wide flange shape, and maybe I'll look at the wide flange shape and the C channel. Basically, the relationship here for case 1, this is sort of a flange slenderness. Flange slenderness is basically B over T must be less than or equal to 0.56 times the root of E over Fy. The root of E over Fy. Where B is going to be the width of the flange, where T is the thickness of the flange, and B is the width of the flange. Well, flange element, I should say, though. And typically what that means, or at least for W sections, that means that is half of the flange width, the overall flange width. Because again, we're talking about the 5 independent elements of a wide flange shape. So if I have let me just draw a few shapes.
Which equation is this?
This is the first equation in the table. This is the first equation in case 1, or this is the equation from the first case of table B 4.1a. This is on, at least on the 15th edition. This is on page 16.1-17. So our W section, draw a C channel, maybe an angle as well. Actually, this is only for double angles. Angles are a little bit different. So C channels, and maybe we could look at double T shapes as well. Okay, so here I'll just go ahead and label some B's. Well, this is B, the shape, this is B. This is B. Again, we're looking at the width of individual elements, not the width of the entire flange. B, 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 and T, T, T. And we'll have a different equation for the webs. T, T, T. So it's fairly plug and chug. Basically, what you do is you just find your limiting, you find your width to thickness ratio. Then you see if it's less than or equal to 0.56 times the root of E over Fy. Very similar again to what we looked at with beam width to thickness ratios. Then I can also look at the web of these. Webs will be a bit more complex. So for the webs of wide flange shapes, so again, it is very critical on this that you make sure to use the appropriate case. You can't just, do not ever just blindly go to this table and randomly throw a pair of dice and pick an equation. You will have a bad day. Whether you're doing this in real life or you're doing it on my exam, you'll have a bad day. So make sure that you carefully read which section you're in, and you make sure that that applies to the case that you're looking at. So if you're looking at, say, the webs of wide flange shapes and W shapes and C channels, that would be case 5. That would be case 5. And I can go ahead and draw these again. Or I can go ahead and draw some this and a C channel. But when you look at the web of, say, a T, then you have to use case 4. Or sorry, not the web, the stem of a T, you would have to look at case 4 rather than case 5. So you just have to be very careful about which case you're using, not to be confused and use the wrong one. Otherwise, you'll have predict incorrect stress values, or I should say predict incorrect limiting width to thickness ratios. And so this is going to be your T, your TW, and we were going to look at the overall H. Well, this is not going to be the overall depth of the beam or the section, but the width of just the, or the height of just the unsupported, unstiffened element. So the height here, this is H here, and this is TW. And the equation that you're going to use, again, very similar, just slightly different coefficients, is that H over TW is less than or equal to 1.49 times the square root of E over Fy. And again, the way we use this as a reminder, if this is true, if H over TW is less than 1.49, then the web is non-slender. If this is greater than this, then web is slender. And then, so how does this end? How do we end up using this? How do we end up using this? Where does this actually connect with? Well, just like we looked at previously, or just as we've discussed a bit, where we end up using this is to determine what section of the steel manual we're in, what section of column, what section of chapter E we're in. And this is the same thing we did with, say, beams. So basically, here, again, if you look at section E3, this is for flexural buckling of elements or of members without slender elements. So section A3 is flexural buckling for members without any slender elements. So in other words, if, and again, this says without any slender elements. So you have to run the check and see, okay, if the web is non-slender, web non-slender, check, and flange non-slender, then you're good. And you can use section E3. If not, then you're going to have to move to some, well, slightly more challenging sections. So, here, at least that's flexural buckling. So, there, if you have, again, now, then if you move though to section, say, E4, this is where you deal with, well, the equations in this section, which are quite a bit more complex than what you're looking at previously. Here, you'll be using this for single angles, and I do want to talk about that. I think I'll talk about this next time. This is for single angles and members. Let's see. Well, I guess this is just another buckling mode. This is just flexural torsional buckling. Sorry, we haven't talked about that yet. That's flexural torsional buckling. We will talk about that next time. More advanced buckling mode. Here. So again, flexural torsional buckling of single angles. And members without slender elements. And so to figure out, so the nice thing at the steel manual is if you're ever wondering what you need to apply where, it does provide abundant language where, whether the section you're looking at applies to what you're considering. So flexural torsional buckling, I cannot manage to write properly. That's torsional and flexural torsional buckling of members without, of single angles and members without slender elements. So let's read the verbiage. This section applies to singly symmetric and unsymmetric members, certain doubly symmetric members, such as cruciform or built-up members, and doubly symmetric members when the torsional unbraced length exceeds the lateral unbraced length, all without slender elements. This provisions also apply to single angles with B over T greater than 0.71 E over Fy, etc. This is just a different buckling mode that we'll consider in the future. But then you also have, later on, there'll be later sections they need to deal with when you have slender elements. So we don't want to, we'll get the section E4, we'll talk about other buckling modes we'll discuss later. Other buckling modes to be discussed later. To be discussed later. But section E7, this is where you deal with slender elements. This is where you have buckling or members, columns with slender elements. And here is where you need to, this is what you do, or this is the section you go to. You go to this section, use this section if one of your elements fails your compactness criterion. If this section, if one of your shape's elements, exceeds a limit, exceeds the limit from B 4.1b, or 4.1a, from B 4.1a. And the equations here are a bit more complex. You can read through those if you wish. I would encourage you to study up on those, but I don't know if we'll quite get to those today. But I think in a follow-up video I'll put together this afternoon, I will look at some of the material from section E4. I need to adjust my notes on some of that before I put that together. So, all right, I think that'll do it for this portion of the lecture. Thank you for watching, thank you for listening, and let me know if you have any questions, and as always, thank you.